That's good. All right.
How do you remove the?
I gotta go. Where's the mouse? There we go. Click on this, so that it works. Perfect. Okay.
And this I need to push here, or is it
No,
open?
I think it's working, right? Yeah,
Alright.
just push it, keep it close to your mouth.
Okay.
Yep. It's hard to tell when everyone else is talking.
Yeah.
There's a manual pointer if you need it.
Yeah.
Okay, so welcome everybody. This is the afternoon session on the multi-phase flows, where they focus on cavitation and boiling. We're gonna start the session with a talk entitled Bore Scale Simulation. Bore Scale Simulations using a 3D multi-phase approach by Mr. Focus.
Yes. Thank you very much for the introduction. Can you hear me? Okay, so as the introduction said, I will present to you our work on pore scale boiling simulations with a 3D multi-phase lattice Boltzmann approach. And what we're interested in is the flow around nuclear reactor fuel assemblies, and particularly in around the CRAD formations. So this you can see an example on the right-hand side, and they are very porous, complex geometries. That what essentially happens is that the liquid that surrounds the fuel rods goes in, then it's boiling within the pores, and it escapes through structures called steam chimneys. And we're trying to simulate that using a thermal multi-phase lattice Boltzmann model implemented on multi-GPU codes. And we're also created an algorithm to generate artificial structures for this CRAD, as getting hold of a fuel rod is not very simple. I will show some results today about some simple boiling domains and some CRAD boiling domains. So this is a schematic of a generic nuclear reactor fuel assembly. So as you can see, it's a complex structure that contains a lot of 4 to 5 meter long rods. And during operation, this is immersed in a pressurized water flow. What we're primarily interested in is the fuel rods. So in there, you have the fuel pellets, which contain the uranium or the nuclear fuel, where the fission occurs. And after the fission is an exothermal reaction, so you have heat being transferred from transferred to the water surrounding. And depending on the behavior of the water, you have two main types of reactors. You have the boiling water reactor, which, as the name implies, you have a phase change, and the pressurized water reactor, which is in a higher pressure, so you don't have vapor at that point. What we're interested in is the boiling water reactor, because due to the boiling process, you have a much bigger buildup of CRAD. Indeed, the boiling is quite important in building these CRAD formations. So these CRAD deposits are formed by the precipitation of metal solutes that exist within the fuel flow, and they occur by corrosion of the tank surrounding the nuclear reactor or the pipes transferring the fluids. And or from injections that try to control the fission. So they are composed from a lot of metals, iron, zinc, nickel. And what happens is that in the cladding that surrounds the fuel rod, which is usually zirconium oxide or zirconia, you have some surface roughness, which then leads to the creation of bubbles. And as the bubble expands, you then have the metal solutes precipitating on the sides of the bubble. And we have in the past simulated the boiling in the zirconia cladding in a 2D case. So as the professor said in the last invited talk, it's very important to get the correct interaction between the material and the liquid. So what we did is we ran molecular dynamic simulations with a piston, so we get the correct pressure on the water, and then we measured the contact angle between the water and the zirconia in its different crystallographic orientations. And we then used geometric series to create a rough surface on which we applied an overheat, and that led to boiling and the generation and the natural generation of bubbles at certain points on the surface. So by measuring the number of these bubbles, we can then get the nucleation site density, which is an important aspect for the macroscopic CFD simulations. And as you can see, we get a good agreement with the experimental results for 7.3 megapascal, although we are running at a slightly higher wall superheat than the experiments, because we're trying to mimic the actual reactor conditions. And what we want now is to move that into 3D. So the formation of the CRAD depends on the position of the fuel rod in the assembly, but it also changes depending on the place in the fuel rod. So with the flow direction, you get a much higher concentration of the fuel rod on top in the higher parts than the lower. But what's important is that the fuel rod affects the heat transfer between the coolant and the cladding. So that because it's a different heat transfer coefficients, you have a loss in efficiency for the reactor operating conditions. But more importantly, it affects the nucleation and retention of bubbles, which creates potential dryouts, in which case the bubble sticks on the surface, and then that can cause higher thermal fatigue on the cladding and can even lead to cracking, which, as you can imagine, is a scenario we really want to avoid. So what we're trying to simulate here is shown in the following schematic. So we've got the porous walls on each side, and we've got a steam chimney in the middle. And we're trying to simulate the water entering the porous structure and creating the boiling and creating the bubble that leaves through the chimney. And we're doing this with the multi-phase MRT scheme that was devised by Lee and Kang in a D3 Q27 lattice with additional buoyancy force and a phase interaction force, an extension of which we're also using to model the interaction with the boundaries. For the energy equation, we're using a finite difference method. So the space derivative is solved through a second order isotropic finite difference schemes, and the time difference is solved through a second order Runge-Kutta midpoint method. And for the equation of state, we're using the Pegg-Robinson with the coefficients derived through the Maxwell construction. Now, the lattice-Boltzmann is one part of the simulation. The other is to create these porous structures. So we have combined two algorithms, the first of which is to create a rough surface domain. So so what we do is, like the 2D, we generate an initial surface with a geometric fractal series, but we then use a Fourier transform to find the spectral density of the frequencies. And we then do a radial average and do an inverse Fourier reaction that gives us a much smoother profile in 3D. And you can see an example here. This is combined with a porous generation, a porous domain generation, with where you use a 3D Gaussian field. Its values we can manipulate according to direction, and we can then set a threshold under which all values are set solid. So you've got the creation of this kind of domains. In this case, we have chosen the direction to be primarily along the heights, so as to closer simulate the steam chimneys. And this is implemented in a CUDA C++ MPI code with a multi-GPU implementation with a 1D spatial decomposition, meaning that this is executed in 40 GPUs, and each of the GPUs is communicating with its two neighbors. And we've been able to run the simulations on the PSDN supercomputer in the Swiss Supercomputing Center. And now more to the results. So this is a simple bubble generation and detachment. So we run this on the BWR conditions, so at a 72 bar pressure with a 17 density ratio and an initial water temperature at 253 degrees Celsius. And at the heated surface here, we apply an overheat of 8 degrees Celsius. And for these cases, I'm using a hydrophilic surface to speed up the bubble detachments. Moving on to more like CRAD-like structures. Here I've got a small porous structure where I've heated the middle. So we have the generation and detachment of one bubble. And you can see it here from the sides. And what I've also done here is to align the porosity along the y-axis, so we have a more steam chimney-like structure. For more complex domains, we have here a CRAD domain with a porosity around 0.5, and I've applied an overheat at the bottom. So what we're looking is the generation of the bubble, and what you can see is that the generation is much faster along the steam chimney in the middle, which aligns with the behavior we have seen in the actual CRAD. And as the final simulation, this is a large-scale domain. We run on 20 GPUs, and we have the generation of bubbles in multiple points in the domain, which, as the simulation progresses, start to merge and detaching. And for this domain, we got a nucleation size density of 6.15 times 10 to the power of 8 sites per square meters, which aligns with the experimental values. So in this presentation, we presented a model for simulation of nucleate boiling flow within nuclear reactor fuel assemblies, and we demonstrate the capability of simulating complex porous 3D domains. And we also saw the effect of the steam chimney bubble nucleation. For the future work, of course, we want to extend the comparison with experimental results and compare with actual rods from the Swiss nuclear power plants. And obviously, the CRAD has a lot of aspects we want to investigate: its porosity, the roughness, the thickness, and the chemical composition. In fact, eventually we want to incorporate the chemical aspect of the precipitation itself. So look at the boiling while the precipitation is happening. So thank you very much for your attention. And if you have any questions, I'd be happy to answer.
Thanks for your very interesting simulations and that presentation. I have two questions.
Yes.
The first one is, did you consider the conjugate heat transfer between the solid phase and the liquid phase?
No, not in this case, we have not. So in this case, we apply a constant temperature on the boundaries.
How to calculate nucleation density.
So in the macroscopic flows, there are equations to calculate something called the bubble departure diameter. So which is the diameter of the bubbles that are leaving the surface. So I'm looking on the surface and measuring the sides that generate bubbles that are larger than this size.
This case, the nucleation site density.
Yes,
Is this input parameter or an output parameter?
it's an output parameter. So I also used, because it's a lot of sites, we've also tried to use an image recognition algorithm to recognize the sites, because measuring them by eye is not possible.
Actually, on the bit of the operating condition.
Yes.
Generated, and that site is comparably the size of the pore in the current. But in this simulation, the bubble size looks like a bit bigger.
So I think in this case is, the CRAD in this case is larger than what you would have in the actual operating plants. The height is high. It's a higher height. Yes, because I wanted to look more also what happens within the pore. So I wanted to increase the height and see the pore and see the effect, the boiling within the pore structure as well. Yes. I mean, so there's two ways we can do it. Like here, I've just done an artificial case in which I just cut a cylindrical shape in the middle of the domain. So, or in the other case is what I did with the porosity, where I align the pores to follow a structure along the height. So you've got more more chimney-like shapes.
You probably said, but I missed it. What do you use to generate the liquid gas coexistence? What is the model that you use?
Can you repeat?
How do you do the liquid gas phase separation? What is the model that you use for the liquid gas phase separation?
You mean the configuration?
Yeah, just how we generate. I mean, just what kind of Lattice-Boltzmann model do you use?
I use the Li and Kang multiphase model, which is an MRT model with a pseudo potential force interface interaction force.
So, thank the reviewer one more time.
Sorry.
So for the second and last on for this shorter than the session, we have Hongyu Ho, who will talk about mesoscopic study of turbulent flow heat transfer and structural cooling chambers.
Yeah, thank you for introduction. Hello, my name is Hoon-Gyo Oh, and I'm from Postech, which is located on the South Korea. And our research group mainly have studied about the thermal hydraulics, such as the boiling and condensation or energy conversion system, and about the nuclear or fusion power plant. So it's very honor for me to introduce my research in this conference. So my research title is Mesoscopic Study of Turbulent Flow Boiling Heat Transfer of Structured Cooling Channel. And I use the term of turbulence to indicate the high Reynolds number flow exceed the 4,000 in spite of the 2D simulation. Yeah, my content is listed in here. And first is about the research objective. Left figure represent the boiling curve, which is very fundamental figure in the boiling phenomena. Starting from the this boiling curve can be divided into the 4 different regions by its characteristics, and starting from the natural convection region, there is the point of the onset of nucleate boiling, and after this onset of nucleate boiling region, onset of nucleate boiling point, the heat transfer coefficient increase, and then they reach the critical heat flux point. This critical heat flux point can be the safety criteria for the boiling phenomena, because if the heat flux exceeds this critical heat flux, then surface temperature abruptly rise and it can damage to the surface. This boiling curve can be changed by the various parameters, such as the coolant condition and species of coolant, and the cooling channel configuration for the flow boiling phenomena. And this full cooling channel is used for the fusion application, and our research group have conducted the experiment with this full cooling channel, and we can draw the this boiling curve. And as you can see in the left figure, the swirl tube and hypervapotron cooling channel has the higher critical heat flux than the compared with the flat channel and smooth channel. And especially the hypervapotron cooling channel has the 34.1% higher critical heat flux than flat channel case. And it is clear that the hypervapotron has higher critical heat flux than the flat channel, but there is some controversy. The controversy of the main mechanism of this enhancement. So numerical approach should be responsible to investigate that mechanism. Several numerical research have been conducted to investigate the boiling phenomena, and Eulerian two-fluid model and VF model are the representative method for the boiling phenomena. However, each method has the advantage and disadvantage, but both methods fail to reproduce the nucleation phenomena. So I think the lattice-Boltzmann method is the most proper method for boiling simulation, including the bubble dynamics and bubble nucleation. And next part is about the flow boiling simulation. And I said that this is the simulation domain for the flat channel and structured cooling channel case. And various methods for the flow boiling simulation are listed in below. And blue and bold keywords are used for the high Reynolds flow boiling simulation and with the structured cooling channel. I will briefly introduce about this with the next page. And I use the slow potential model with the D2Q25 isotropic scheme. And I also solve the temperature with the finite difference method with the D2Q25 isotropic scheme with the Runge-Kutta method for the time. This is about the wire boundary treatment, and Red developed this regularized boundary method to enhance the stability at the boundary node. And they found that this regularized boundary method has higher stability compared with the Juhe boundary method. And I add the forcing term with this regularized boundary method to represent the wetting method and fluid flow interaction force at the boundary node. And I tested the various boundary treatment method with the boiling simulation, and I can get this figure. As you can see in this figure, the finite difference method can achieve the highest Reynolds number for the flow boiling simulation. And next part is about the unique conversion of lattice-Boltzmann method. Unique conversion in lattice-Boltzmann method is same with the Buckingham's phi theorem. However, delicate conversion process should be needed because there are the upper limitation of velocity and lower limitation of viscosity in the lattice-Boltzmann method, and we should consider the relation with equation of state parameters. Conventional method use the reference length scale and related dimensionless number to convert the unit. And capillary length scale and Reynolds number is widely used for this. And this method use only two equations for the four free parameters. So this cannot wholly consider the conversion relation. And novel approach considering all conversion relation with predefined parameters such as the repulsion parameter or attraction parameter, gas constant, and surface tension of equation of state. This can consider use the four equation for four free parameters. So it can convert the whole relation, but it has too low conversion factors, so it needs the massive cost to simulate the millimeter scale simulation. So I proposed the necessary approach which matching the necessary condition for the interested hydrodynamic phenomena such as the bubble departure diameter. And this necessary method use the three equations. So it has the single pre-parameter, and I can lower the 1,000 times the lower number of nodes to simulate the millimeter scale simulation. This is the test case of the flow boiling departure diameter. And as you can see in this slide figure, the conventional unit conversion method could match the specific point of the departure diameter according to Reynolds number. However, it fails to match a wide range of the departure diameter of wide Reynolds number range. Contrary to this, the necessary unit conversion method can match the departure diameter within the wide Reynolds number range. So this necessary method is adopted to for the turbulent high Reynolds flow boiling simulation. And next part is about the outlet boundary treatment. I use the characteristic boundary condition, which is the widely used in CFD community and LB community to sustain the stable bulk flow. And this characteristic boundary condition can minimize the non-physical reflection at the boundary node. And non-reflector outflow boundary condition is used for the inflow wave magnitude at the outlet boundary node. And some benchmark tests are conducted, and this is result of the vortex passing test. Vortex is initialized with this equation, and as you can see in the left figure, the convective boundary condition and characteristic boundary condition shows no distortion while passing the vortex passing the outlet. And to investigate the continuous effect of outlet boundary condition, the vortex threading onto square box simulation is conducted. The reference data is extracted before the vortex passes out the very long domain with the convective outflow boundary condition. And as you can see in the right figure, the convective boundary condition makes undesirable pressure drop after the vortex passing the outlet. Contrary to this, the characteristic boundary condition can keep the constant pressure while vortex passing. So for the continuous flow boiling simulation, I adopt the characteristic boundary condition for the outflow boundary treatment. And this is the simulation result of flow boiling simulation, and heat flux level is shown in the left black box. For the flat channel case, at the first stage, the superheated fluid departure from the heated surface, and as heat flux increase, the nucleation occurs near the heated surface, and as heat flux increase up to the 500 kWm², the nucleated bubble slide along the heated surface and merge it and lift up the bulk flow. Different with this flat channel case, the generated bubbles are pinned for the structured cooling channel case, and this bubble merged and grown without escaping the cavity. Yeah, and the continuous boiling simulation is conducted without any divergence with previous various methods, and we can find the distinct boiling characteristic according to the channel configuration. For further explanation, I captured the characteristic scene of the flow boiling, and left figure shows the result of the flat channel case. For the flat channel case, the nucleation occurs at the heat flux level of the 450 kWm². And as heat flux increase, the 500 kWm², bubble sliding and merging and lift up to the bulk flow. And at the heat flux level of the 550 kWm², the merged vapor blanket covers the surface, and it causes the abrupt temperature rise. With the surface temperature data, we can identify the critical heat flux of the flat channel case, and I compared this result with the experimental result, and I can find that the LB critical heat flux result are matched with the experimental correlation within the similar order of magnitude. And for the structured cooling channel, you can see that the nucleation is delayed in terms of the heat flux. As you can see in the right figure, the first nucleation occurs at the 550 kWm² of heat flux. And as heat flux increase, the bubble pinned at the corner, and this pinned bubble grown and emerged in the cavity, and it cannot escape easily for the structured cooling channel. And this phenomena can be found in the experimental result, and with the LB simulation, we can reproduce the bubble dynamics similar with the experimental result. And we also identify the critical heat flux by the surface temperature of structured cooling channel, and it can be found. It is identified that hypervaporatron has the higher critical heat flux, about 27.3% than compared with the flat channel case. And this result is also comparable result with the experimental case. So in some researches insist that the vortex flow in the cavity help the bubble escape the cavity, so it can enhance the critical heat flux. However, for the simulation result and the experimental result, the bubble is trapped into the cavity. So I drew the directional heat flux map to find another mechanism of the critical heat flux enhancement. And left figure shows the directional heat flux map. And in this case, the incident heat flux is the 600 kW/m². And as you can see in the left figure, the local heat flux of cavity bottom is lower than the incident heat flux, and heat is distributed to the fin structure. This heat distribution occurs near the interface, so it is hard to investigate this phenomena with the experimental result. So numerical approach should be responsible to investigate this 2D conduction effect of the structured cooling channel. And this is my conclusion. And LBM could reproduce the turbulent flow boiling phenomena with proper some hydraulic characteristic, and structure channel has higher critical flux compared to the flat channel. And heat distribution is the main advantage of the structured cooling channel. And local and global thermal hydraulic characteristics are different in structure channel compared with the flat channel. Yeah, thank you for listening.
Thanks for your interesting simulations.
Yeah.
So it's very interesting to see you use the characteristic of boundary condition
Yeah.
in the traditional set. And that is both my simulation.
Yeah.
So my question is that is this boundary condition suitable for the case where the bubbles are moving across the boundary?
No. This is very good question, and I adopt the intentional condensation zone to prevent the bubble touch the outlet boundary. So yeah, I think that is the next step to develop this characteristic boundary condition with the generated bubble pass out without any divergence. Yeah.
Simulation bubbles is going to be shrink.
Yeah, I adopt the intentional condensation zone, and this method, I think this method is widely used for the flow boiling in the CFD. So I benchmark this initial intentional condensation. Yeah. Yeah.
For the non-reflecting boundary condition.
Oh, please, one more time. Yeah.
The non-reflecting boundary condition.
Yeah. Yeah.
Gonna work for a non-ideal pressure.
Yeah. It also works for non-ideal case. Yeah. Yeah. I use the regularized boundary condition same with the boundary treatment, and I define the macroscopic density and velocity with this characteristic boundary condition, and I define the unknown distribution with the regularized boundary condition.
Yes. I noticed that the information is mostly in the water.
Yeah.
Wonder if they have played with the surface permeability and see if that changes if you choose contact angle.
Yeah. I think that contact angle can change the nucleation position. Yeah. I think that if contact angle decrease, nucleation occurs not at the corner and near the corner. Yeah.